Thank you for joining us today at the University of Washington Data Science Seminar. This is our third talk in our special series at the UW Data Science Seminar featuring the AI at UW project presentations. To remind you again, these projects partner domain scientists with experts specializing in AI theories and methodologies. And the eScience Institute supported these projects in collaboration with Office of Research, the Paul Allen School of Computer Science and Engineering, the Information School, and the NSF Institute for Foundations of Data Science. John Choe is today with us, an associate professor of industrial and systems engineering at University of Washington, and also the director of the Disaster Data Science Lab and the deputy director of the Center for Disaster Resilient Communities. He received his PhD in industrial and operations engineering and a master's in statistics from the University of Michigan in Ann Arbor. His work has been supported by the National Science Foundation, National Institute of Environmental Health Sciences, Centers for Disease Control and Prevention, and other public and private sector organizations. And today also we have three other collaborators, amongst them Kevin Jamieson, an associate professor in the Paul Allen School of Computer Science and Engineering at the University of Washington. His research explores how to leverage already collected data to inform what future measurements to make next in a closed loop. His work has been recognized by an NSF Career Award and Amazon Faculty Research Award. He received his undergraduate degree from the University of Washington, master's degree from Columbia University, and PhD from the University of Wisconsin-Madison, all in electrical engineering. Welcome to our seminar, and I'm looking forward to this talk. Again, the third in our series. The title of the talk is Data-Driven Optimization of Stochastic Computational Experiments, Applications and Hazard Risk Assessment. Thank you so much for being here today.
Thank you so much for your introduction, Nicoletta. Hi, this is John Choe. So nice to see you all here. This was really fun collaborative project with folks from Allen School, including Professor Kevin Jamieson here, and also our students, Ethan and Cash over here. Other students graduated, so they make it. Overview, just quickly, we're going to start with some motivation behind this work, and then theoretical development behind the algorithm that really empowered this project, and also empirical validation of the algorithm that we went through for hazard assessment related. And then we are going to talk about the results, discussion, and conclude the talk. Just as a general motivation here, computation experiments are ubiquitous, and many of you actually know Dr. Richard Hemming, who is the third Turing awardee at Bell Labs back in 1950s, said that at present, we are doing 1 out of 10 experiments on the computers and 9 in the labs, like physical labs. But before I leave, it will be 9 out of 10 from the machines, which are computers. That was his prediction back then, and back again in 1950s, and he was not believed by those leadership members in the Bell Labs, which was really powerful, powerhouse for science and engineering. So by the time he was leaving around 1990s, already his prediction was proven right. Computation experiments nowadays are really considering stochastic aspects, randomness and uncertainties, because that's what really works. For example, wind turbine reliability evaluation need to consider the randomness around winds, aircraft, extreme weather events, nuclear reactor reliability evaluation. We do need to consider uncertainties in our computation experiments. That make computation experiments way more expensive to do a good job in understanding the real phenomena. In this project, we were focusing on motivating applications in disaster management. I see this Zoom is really hindering your view. I'm trying to see whether we can hide it so you can see a little bit better, ideally.
Down, yeah.
There we go.
So this project
was largely focused on motivating applications of disaster management, thereby we could potentially save lives and also billions of dollars for property losses and so on. Now my clicker is not working. Once with the mouse. Once with the mouse, and that will always work. Great. So a lot of hurricanes, tropical storms, we have been experiencing that over the past several years. Increasing intensity, increasing frequency, I believe you all have sort of observed that or noticed that. Wildfires are becoming more frequent, more intense, obviously, and also back in 2020, we have also experienced pandemic. All these kind of disaster applications can benefit from computational experiments that consider randomness in them. With the context, we were largely focusing on geotechnical hazards. So here you are looking at ring of fire or Pacific Ring of Fire. You probably heard about the 2011 Tohoku Great East Japan earthquake event, which created giant tsunami. Over there, oh, where's Japan? Oh, over there. And also Chile, Tonga earthquake. So later, our students are going to talk about some validation work around this area, Tonga area. But in our region, in Pacific Northwest, we are also sort of preparing for large earthquake that could be quite similar to Tohoku earthquake that happened back in 2011. Prediction of seismologists is that within the next 50 years or so, they are looking at around 7 to 15% probability to experience similar magnitude of earthquake, which is about 19-fold. Huge earthquake. Once that kind of earthquake happens, we could sort of expect tsunami. So tsunami hazard assessment is one of the major motivating applications for this particular class. Black screen, that's another. Oh, here's a video.
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next: run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesanuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall into Kamaishi City. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing. When two tectonic...
It was a major disaster in Japan, but again, it's our Pacific Ring of Fire. Our region also expects similar magnitude of earthquake. So that's why we are working on this particular project to make sure that we can better understand and accelerate the overall computation experiment to do a better job in assessing the hazard risk related to tsunami. All right. Specifically to formulate this as a mathematical problem, here we are looking at different earthquake scenarios. And specifically, we want to understand which earthquake scenarios we want to simulate to better prepare for tsunamis that could exceed a certain height or certain level. Like, there could be many different scenarios, random scenarios based on past events. Like in this case, we are looking for our empirical evaluation. We are looking at this Tonga Trench area, which is close to Australia. So again, over context, using computational experiment, we want to figure out which earthquake scenarios we should focus on to better prepare for tsunamis that could be really disastrous to our region. All right, with that context, I'm gonna hand this over to Kevin.
you. Thanks, John. Good afternoon. I'm Kevin, in the computer science department. I work on machine learning and specifically the statistical side of things and how to collect data optimally. And so the way that we're going to model this problem is that these earthquakes have initial conditions. Okay, so how offshore was it? How deep was it? What was the land formation looking like in that particular condition? And we have historical data on how these earthquakes can form, and we can also sort of approximate how these form and have some idea of how frequently they happen. And so what we're going to do is we're going to model nature as forming some initial conditions for an earthquake. These initial conditions are going to model as X, drawn from some distribution P. And this is basically how frequently do these initial conditions occur in real life. And then given that earthquake event, you're going to have some resulting tsunami. And where that resulting tsunami is going to go through is going to be some function of X, the initial conditions, which is going to be some height, so the height of the wave. And what we're trying to do is estimate basically the threshold of what is the probability that this wave height gets above some certain value. I've chosen 0 here just arbitrarily. I can always add a value on both sides. It doesn't change the problem. So I've chosen 0 just as a default value. But what we want to do is essentially, given some initial conditions, the probability distribution over the possible initial conditions, we want to estimate the probability that a wave height exceeds some value, such as that 18-foot seawall that destroyed that city. We want to estimate this probability. The issue is that while we do have a simulator, f of x, a computational simulator that given an earthquake, we can estimate, run this simulator out, it can give us some wave height at each location on Japan's coast, for instance. However, the issue is that the simulator can be extremely costly. Physics simulators can run, take seconds, minutes, hours, or even days or months. Weather simulators, for instance, can take days to update. That's why we have such sometimes delayed weather forecasts. So we have this physics simulator, but it's costly. We don't have a lot of access to the simulator just because it just costs money and time. But for any initial condition that we want, we can run it through the simulator and get a resulting tsunami simulated. What we want to do is estimate this probability of this bad event. Now, since we have this probability distribution, we have this simulator, the most natural estimator you could think of is just to draw x1 through xc initial conditions from our distribution P, run each one through our simulator, get the wave height, and then just count the number of times that the wave height exceeded this threshold value. This is a perfectly fine estimate. This worked quite well and certainly converges. However, it can be extremely inefficient. It can be inefficient in that if getting a wave height above that threshold is very, very rare, that means that your ability to estimate this probability accurately is very, very difficult. So as just an example, suppose the probability of exceeding that wave height is very, very small, like with alpha, say 1 e to the -6, just insanely unlikely to happen. But given enough trials over time, you are going to see this thing happen. If we wanted to estimate this very rare event up to some relative error, let's say 10%, plus or minus 10%, then we would need a number of samples. The number of simulations you would need to run would be something like 10 over alpha, whereas alpha is equal to 1 e to the -6. We're talking about 10 million simulations of this. And again, you should think of these simulators take like an hour to run. So this is completely infeasible. Faced with this issue, people have developed machinery to deal with this. So one common way of dealing with this is to take a Canada distribution Q. I'll tell you how you define this in a moment. Draw x1 through xc from this Canada distribution Q. Try this alternative estimator, the importance weighted sample. This is an unbiased estimator of alpha still, but now weighting it by P over Q. And if under that same situation of a very, very small value of alpha, if I choose my Q appropriately, if I choose this Q function very, very intelligently in a very nice way, we can then have that relative error just as before, be less than 0.1, but now I only need to say 100 simulations versus 10 million. Okay? And so there's drastic speed up, which is amazing and great. The catch is that how the heck do you define Q? Because if you look at what Q is defined as, it requires knowledge of F. The whole point is we don't know what f is. We have to go and run the simulator to find out what this value of f is. And so we can't actually define q. But what's going on? How are we getting this data? Well, let's have a plot here. On the x-axis is the x variable, the initial condition. It's just a doodle, just a one-dimensional example. And then we have this function f of x. Then we have our threshold here at 0. And we're trying to find those locations where f of x exceeds that threshold. So it's just this region here and this region here. Our probability distribution P is down here. And what we want to do is basically we want to sample from this distribution P or estimate the mass on this distribution under this distribution P only where this function exceeds that threshold. So between these two lines, we want to basically count up this mass because that's where the function actually exceeds this threshold. That is the probability of that wave has exceeded, right? And so ideally what we want to do, the whole difficulty of this problem is drawing samples that are in these narrow bands of probability. This is a very, this is a doodle, but in real life, this could be, in 1,000 dimensions, and you can see these probabilities, and they're very, very small. It could be 1 to the -6, just saying in the grid. And so what we want to do by defining some Q function, some Q distribution, where it only has large mass around these places where the event occurs, where f of x exceeds the threshold, then by using that, we're very likely to get samples in this very interesting region, and then we can get a gain, and we can estimate this probability with very few samples. The issue is that estimating or defining a nice distribution Q requires knowledge of f. And so there's this chicken and egg problem. So what our approach is basically, we have another function here. So blue is the true function here. I've changed it up on you a little bit. And now, again, we're still trying to figure out where this function f exceeds this threshold, this zero line here. And after what we're going to do is we're going to take some amount of samples. We're going to choose some x's in this domain here. We're going to get some values of f of x, and we're going to estimate f of x by doing a simple regression. Okay. And now, after we get that regression, we can build confidence intervals using statistics so that we can get a lower bound and an upper bound on our f of x. So we can tightly sort of sandwich the true value of the function f within this sort of lower bound and this upper bound of what we can measure. And then we do, using this estimate, just as lower bound, we can then define our Q function that way and estimate an alpha hat. Okay, so this is one way we can get this Q function. An alternative way of estimating this is just if we have a lower bound and upper bound on our f, we can then just, because we know what P is, this is the thing we're trying to, we have access to P, we can just compute an upper bound using our lower bound on f and our upper bound on f and get upper and lower bounds on this probability that we're trying to use. But again, the problem is, how accurate does f bar have to be? F lower bar and upper bar. And how do we estimate it? And so the approach that we take is to model our function f as a linear function of some nonlinear feature map. And so what we're going to do is, whatever these earthquake conditions are, we're going to map it to some very high dimensional space. And this high dimensional space, this nonlinear feature map, could be expert defined, meaning domain scientists is defining exactly what the important features are, what makes this earthquake going to have its effect on a tsunami. Or it could just be smooth features that are universally good approximators. But in any case, we're going to model f as this linear function using these nonlinear features. And we know there's only an approximate model. It's not going to be exact fit, but it's going to be good enough. But the beauty of using an approximate model like this, we can use the theory of linear least squares to know that if we just use the least squares estimator, we have this error. So this is our error estimate. There's a true error. This is our estimate of f, and this is the true value of f. And what we're trying to do is figure out what is the maximum error over our uncertainty region. The uncertainty region is exactly these points here, where the function, the upper and lower bound are going through that threshold that we care about, that magic threshold. We know all here the function f is below the threshold. We know over here the function is above the threshold. But during these uncertainty regions, we don't know. So we need to go sample more. And so this is the error that we care about. We're going to reduce this error. And what least squares tells us is that we can use statistics. It doesn't matter what this functional is if you don't recognize it. But what I want you to recognize is that this is an up or down on the air, and it is a function of the measurements that we took. Okay, it is a function of x1 through xt, these initial conditions that I'm going to go take and measure. Okay, but it is not a function of the observations yt that take that very expensive simulation. Okay, so what that means is that we can control our error. We know what the error is going to be before we've even taken a single measurement. This is pretty mind-blowing the first time you see it. And this is the idea behind this is optimal experimental design. This is a field of statistics pioneered by Fisher in the early 1900s that is now responsible for many engineering processes and agricultural designs. But the point, we're going to leverage this machinery to have an adaptive procedure. We want to be as efficient as possible, use as few measurements as possible. So what we're going to do, we're going to pick measurements to minimize the error on this uncertainty region U, observe those measurements, fit R theta hat or F hat, and then reduce that uncertainty region U with that more tight bounds, and then repeat this process over and over. This is a lot of math. So we defined theory and things because in our field, what we try to do is try to quantify exactly how many samples are necessary. How do we know we're doing a good job? And all this theorem says, you don't need to read it. All it really says is that this procedure that we've defined and the algorithm that we defined that you're going to hear about later is actually provably optimal. Meaning there is no other procedure out there that can do substantially better than ours in the sense that it will not take many fewer samples. And really what we're doing here is to get around this rare sample problem. What we're doing is we are exploiting the fact that this function f that we're trying to learn that exceeds this threshold is smooth. And so we're trying to trying to find this needle in the haystack problem for trying to exploit the structure of f so that our sample complexity, the difficulty, does not scale at all with how rare an event is. And here this is my last slide. This is just a little doodle. You'll see some more interesting realish more data in a moment from the students. But what this basically says is that it works. Okay, no surprise there. I would not show you a plot showing our stuff does not work, of course, but it really does work, and yet you'll see this in the next several slides.
You before me slide.
Good.
Okay, so for our case study, specifically, as discussed before, we're looking at sampling around the dangerous scenarios for tsunamis, as this is a big problem in disaster science, as there's a lot of natural epistemic uncertainty involved when predicting scenarios, such as tsunami max height. And essentially, this is a problem that we're looking at through approximations. And a problem this is a problem that's being looked at through the probabilistic tsunami hazard assessment, which is essentially something like looks at this problem through two sides. One is through trying to simulate dangerous tsunami scenarios, and the other is through optically sampling which scenarios are most likely to be dangerous, as running these tsunami simulations is very computationally extensive. So this is what we're looking at doing MELP for. As MELP can use informed sampling with machine learning, as discussed before, to kind of use an explorative approach to sample directly for the dangerous scenarios without having to run all of the less important scenarios which are not dangerous at all.
Yeah.
Yeah, and so the place we source our data from is from Australia's PTHA. So they conducted a nationwide PTHA analysis on tsunamis around Australia in 2018, and that data set is named PTHA 2018, effectively. It has quite a few scenarios, but most of them, while they do have max stages at certain points, they aren't onshore simulations, which are significantly more costly than offshore simulations. We'll go into a bit more detail later. Like Kevin said earlier, onshore physics-based simulations can take upwards of days to weeks to run, and offshore, usually within a day, around a couple hours is the time frame you can estimate for those. But still, this is only feasible through this data set because we didn't go through the setup of the simulation, also all the parameter training you need for that. And so the way we treat this data set is that every time we reference a value, we count it as if we call the simulator themselves. And so there are, as I said, there's two different types of simulations. There's offshore simulations, which are a little cheaper and are what PTHA consists of. And then there's onshore simulations, quite more costly to run, mostly because once you're near shore and near land, you have to take into account land height, any landmarks, any obstructions in the way, and the physics for all the collisions that takes that into account are quite expensive and result in the super high computation costs. The way we're using now is that given those offshore simulations, if we can determine that some earthquake scenario results in a wave height pretty high offshore for a cheap cost, you can kind of use that information to make your subset of scenarios for onshore simulations way smaller. And so you have less wasteful resources dedicated to onshore simulations as the potential scenarios you simulate are way smaller. And that's where our sampling comes in.
So before we continue, we're going to talk about some common trends that we'll be bringing up later, which are important for this case study, and specifically for the PTHA 18 data set that we're using. So firstly is the hazard point. Essentially, this measures the individual point at which we're measuring the impact of the earthquake scenario causing tsunami. This is where we get the resulting tsunami data. So the specific coordinate point X and Y of, say, what's the tsunami max stage. Next slide. And for example, the max stage is what we're primarily using. This is the peak water level from the mean sea height to the top of the tsunami, which is essentially just the height of the tsunami. This is primarily what we're using to measure whether the tsunami in offshore is going to have a large impact once it reaches the shore. As well, a bigger tsunami offshore is going to have a bigger effect once it reaches land.
Yeah. Next, we have the source zone. The source zone is a collection of subfault or subfaults that are placed upon a single fault line or lines. This is just a large collection of subfaults that are places along the fault line that can rupture or slip, and these result in like what causes an earthquake to be dangerous and what causes the waves to increase. And then each one of those ruptures gives us a slip value, and these slip values can be used to determine how a tsunami will, or are determined for those physics-based tsunami simulations.
So the method that we're mainly comparing this to is via a paper by Gareth Davies using a method called stratified importance sampling. It's a combination of importance and stratified sampling to try to selectively sample the most dangerous scenarios. Essentially, what this does is it first separates all the earthquake scenarios into different strata of magnitude. So usually varying in bins of 0.1 from around 7.0 to 9.0 and higher. And then afterwards, after separating these, when it samples from each individual strata, it uses a pre-computed importance function, which is just defined as IFD is the maximum stage of a tsunami at a scenario at a nearby state on the nearby site T. And how this works is essentially first they have all the pre-computed data for this other site. At this different site, they then adjust the weights at which they want to sample each scenario. They use this equation here, which is positively correlated with the height of the tsunami, as well as the original occurrence weight of said scenario. And based on this, they use it based on all the scenarios that they managed to sample, which are going to be ideally the most important ones, the most dangerous ones, they're going to calculate what's known as the exceedance rate, which is a sum of the occurrence rates of all the sampled scenarios, which is going to be essentially the probability that such a dangerous scenario is going to occur. And as we can see here, we have a bit of data from their paper. So one of the problems with stratified importance sampling is that it requires pre-computed data at the previous site, which in many of the sources we're using is a lot of samples. But however, it has really good effects on nearby sites. As you can see here, one thing they compare to is uniform sampling as well as just stratified sampling without the importance function. And it has a very good variance reduction ranging from 2.57 to 3.09 on nearby sites, which basically means it's just reducing the variance by a factor of that value. And so you can basically measure the importance function on one site, and then all the nearby sites are generalizable very well. However, distant sites are poorly generalizable. As we see on this site, distant site NZ is just a very far away point that has a variance reduction of 0.495, which means it's worse than stratified sampling at that case, because the model is no longer, the importance function is no longer accurate. Wow. So the reason that we're mainly using MELP over stratified informal sampling in this case is because since stratified informal sampling needs this pre-computed data, it's good for this case study where we already have the PTHA-AT. However, if you're trying to measure this for a location that doesn't have this data already existing, then you would first need to pre-compute the maximum stage for every single earthquake scenario, running the simulation, the offload simulation for each of them. And then after that, you could generalize this function to nearby sites very well. And then you would have to do the same process again if you would like to do a different part of a scenario. However, using machine learning and criminalization, MELP is able to do this without using any pre-computed data. Simply taking in the initial earthquake scenarios, it's able to use this explorative approach to sort of query the simulator directly and kind of model the function based on that. And then dynamically pick the scenarios that are most likely going to be dangerous.
Yeah, so Kevin already talked about most of the draft variants, so we'll mostly focus on what the changes for we're specifically applying to this case. So there's 4 main points of contention here. One of them is the earthquake scenarios themselves. This is based off of the slip values and a bit of feature engineering we did that we'll touch on later. Then we have Q of E, which is the max stage that we call from the PTH18 set. We'll essentially determine this as calling the simulator itself, which is what would happen if you didn't have a pre-computed data. And then you have Q of T. Q of T is the threshold that determines if something's dangerous or not. The example Kevin gave was 0. We'll probably use 2, which is what the SIS paper used, since we're using their source zone and their hazard points as reference. And lastly, the recurrence rate is given by the data set itself, and those aren't too hard to compute as they're given by the earthquake scenarios, not the tsunami scenarios. And then, as we can see, MELP turns out to be quite efficient in approximating our exceedance rate, which is the sum of all values greater than our threshold. So we end up being, if we just take the pre-computed data, make a simple if loop, and then get all the values, or out of all the exceedance rates, you essentially get the same value that MELP gets with a difference of 0.81%, which is really good, as we can see right here.
And so the other benefit that MELP has is if we're looking at SAS, which first requires pre-computing for this source zone, 44,685 different earthquake scenarios. And then afterwards, you can sample from the importance function. However, MELP only needs approximately 7,000 scenarios in each case, or one of our runs was 6,293 sampled scenarios to get the same exceedance rate value, which computationally is much, much faster. As each offshore simulation, while much faster than onshore, can still take a fair bit of time. And essentially what we also found out through running MELP is it had an accuracy, precision, and recall of roughly 99% out of the 39,000 scenarios it was able to sort of categorize. Out of all those, basically out of the 44,000, it took 39,000 scenarios and it was able to correctly put them into good or bad categories. And the remaining scenarios were still pretty accurate within the predictive function that it had.
Yeah. And then one other comment, suppose for a very awful sense that this sampling or a calling of the simulator only took 3.5 seconds. Unless it's slower than 3.5 seconds for each one of those simulations, then SAS could be faster. But as soon as you get above that 4-second mark, MELP beats it with our pretty rudimentary implementation of it and could be optimized way further to especially be way more efficient in that case as well. And so one of the things we want to point out while we're going through this case study is that feature engineering helped a lot with MELP. So initially we assumed that increasing the input size of the vector would be quite harmful to this performance because we're already at a vector of slip values of 200. If we add a distance to each one of them, that double it, making it 400. But this turned out since we were able to give the function more information to base its values on, there's also much faster learning and much faster convergence on the true function it's trying to approximate. And so what I can see here is an example. Initially, we had just the purple values, which was the slip value of each subfault. And later on, we added the gray values, which is the distance from that subfault to the hazard point. And this allowed it to learn the function more as, especially if a subfault is close to a hazard point, that was way higher. And that's easier to learn than having to take more and more samples. And this also reduces the number of samples we need. And so this gives us another benefit of MELP, which is the scalability and adaptability. We initially were worried for the large input size, and we were worried that MELP couldn't approximate this solution. But even with that 400 value input vector, it did quite well, as we saw earlier, with a very with a significant reduction in the number of samples and also a really good estimate on the antecedent rate. This kind of adds to the adaptability of MEL, as for example, mentioned earlier by John. If you look at the simulations for pandemics that a lot of universities and a lot of companies use during the pandemic era, you have a simulator that takes in parameters that determine the start of infectious disease. And then once you run the simulator, it gives you an output for how likely that turns out to be a pandemic. You can use those input values for the simulator itself as the input values for MEL. And then it will slowly try to get that function, learn it on its own, and be able to approximate what kind of scenarios and what leads to a pandemic. And that could be another possibility of MEL. Well, lastly, we're also trying to explore new ways we can apply MEL in disaster data science scene, and we'll give that to John right now.
All right. So another application for MEL could be useful for many different stochastic computation experiments. But at the moment, we are talking to the researchers at Tohoku University, which experienced, again, 2011 Tohoku Great East Japan earthquake. So for that application, we are talking about how MEL could be useful for assessing the impacts of landslides, which could happen after tropical storms or some winter storms or after earthquakes. So this is a video about landslide that happened in Washington state. So we can make a case that this kind of study could be really relevant to the region where we live and work.
Well, it was 10 years ago this week when America's deadliest landslide took the lives of 43 people in Oso. The event forever changed Snohomish County and the countless people that are still connected to that tragedy. Jake Wittenberg is back to join us to discuss this. So, Jake, you were one of several journalists who covered this when this happened.
Yeah, myself and several of our colleagues that were called out there day after day for the grief and despair of the Oso landslide. And all this week, we're looking back at what happened and how things have changed today, 10 years later. Here's a preview of what to expect tonight at 6:30 and 11.
There's like a mudslide and everything's gone. The houses are gone. We watched hundreds of trees come falling. I'm on Steep Post Road, Highway 530.
10:45, the call came in for a roof in the middle of the road. Kind of a strange call to get, but it wasn't a real big call as far as what I could tell on the pager.
And there has been a huge landslide, and it's pushed the house all the way across the road.
I was thinking to myself, if there's a roof on the road, I might need to cone off the road. You never know who's around on Saturdays. They're all volunteers, so they got family stuff.
Basically, it's for a single engine response, that they have water in the roadway and that a part of a building. And so it's like, okay, a little slide, something has blocked the highway.
Wow, it's really flooding.
And as I pulled over the hill and down into where the road was blocked, nothing really made sense.
There is a structure out in the middle of 530. We'll be investigating.
I had recognized it from a barn that was off to the south of the highway. We're getting on the radio and asking questions and not really getting any information.
We're hearing cries from somewhere over there. Are you guys hearing them from your end?
I'm Sergeant Rocky Oliphant with the Washington State Patrol. I was the first trooper on scene of the Oso landslide. So I was on I-5. I was actually checking for speeders. So I was the only one headed out there. And so I came around a corner. I'll tell you that when I arrived on that scene, it was an overwhelming feeling for me. I tried to get over my radio to tell my dispatcher what was going on.
He's going out for search and rescue helicopters. This is a major event here, and we're going to need additional resources.
You could start hearing on the voices, well, where are you? We don't see you.
I want you to go to the end of Whitman Road and see if you can see the people that are trapped on the other side of the water.
Back and forth, and all of a sudden you kind of realize, well, if they're not able to see or make connection to each other physically, this is much bigger than any of us realized.
It just goes to show you, 10 years.
All right. So as I mentioned, landslide risk assessment is another use case we are currently looking into as we make progress on tsunami hazard assessment. So we are talking to the researchers at Tohoku University. They have data, a lot of the data on landslide. due to typhoon over there, and also due to a lot of seismic movements happening over there in Japan. So basically what we are trying to do is optimizing this simulation experiment to better allocate computational resources to understand which area will be more riskier than the other areas. So that way we can identify where to allocate resources to better assess, prepare for, and respond to landslide events. So that's another application that we've been looking at to looking at as an application of the Melk algorithm that Kevin talked about. Yeah, we just skipped the future work. So if you're interested in other directions for future work, we'll be more than happy to talk about that. But still, I do want to leave some time for Q&A since we have about 7 minutes left at this point. So at this point, I'd like to thank our sponsor, AI UW, Seed Grant Award, and also National Science Foundation that made this research collaboration possible. And also thank you so much for your participation and attention today. Thank you.
Thank you so much. This is great work. Please, if you have any questions and online, please use the Q&A box to ask your questions.
So two questions real quick. How is the complexity of the algorithm? Do you guys have a lower in terms of data for where it's still able to function? Basically it's state of the art.
Yeah, so we do have very tight upper and lower bounds on the number of evaluations of the function to find the level sets, the points above, below threshold. So that's very well characterized. In terms of the computational complexity of the algorithm, basically it runs, it'll run basically a logarithmic number of convex programs. So, it's going to be Pauli in the dimension and the accuracy of that optimization problem. But basically, if you're in D dimensions, it's safe to say running Frank will be near down to order D or D company.
There was the discussion at the approximation of the function in question as I guess a dot product of your px. How do you choose that px? Like, is it arbitrary or is it?
Yeah, it's a great question. So, like in this case, the px was engineered by domain experts that could look at the features and come up with a good feature representation that would have that linear structure to it. In general, when you don't have such insight into what the functional form is going to look like, you can use the equivalent of so we call it random features, but basically what this is amounts to is like doing a kernel approximation in that kind of RKHS function space. So basically, any smooth function we can approximate, and there are ways to define those smooth functions appropriately. But of course, there's no free lunch. The more sort of complicated you want your function to be, maybe the less and less smooth, the higher and higher the dimension is going to be. And so the larger it's actually going.
So at the beginning of the project, we spent a good amount of time to make sure that our app is smooth in general in our design space to make sure that Melk will work well for this problem. That's why even over 400 dimensionality for our input, using only around 6,000 to 7,000 samples, we could still get very accurate.
Yeah, so the dimension for the earthquake problem, the dimensional space is the number of subfaults you have, or how do you put the dimension?
So the dimension of the space is originally just the dimension of how many subfaults there are in the source zone. In this specific case, there were 216 subfaults. However, we did a bit of feature engineering to improve that because it was quite, it's quite a sparse data set. So we also added the distances from the subfault to the hazard point itself. And so in total, the the dimensions is about 200, what's it, 432.
Yeah, you're right. It does follow the number of subfaults in the scenario.
That's the question. I saw that you guys are using the probabilistic tsunami hazard assessment. We also have the probabilistic seismic hazard analysis when we're looking just for earthquakes. And usually you look for, like you said, the distance, the magnitude, and some other key important characteristics of an earthquake when we're running that analysis. How do you run that? And is that like, when you run the program, are you targeting a specific location? Or like, are you just running in Seattle and seeing ground motions that match?
Yeah, so the idea is that you could do that with the current setup we have with Mel. Currently, we didn't want to deal with going through the simulation process, so we just used Australia's PTHA data set. But to be fair, our input isn't very feature engineered. The only things we have is the slip values of the subfaults. So once an earthquake, like you can, these scenarios aren't measured necessarily, they're generated. It's just a permutation of all possible earthquake scenarios. And then the one part that's computed is the recurrence rate of each earthquake scenario. And that's taken as the average as a bunch of the average of a bunch of simulations that estimate that recurrence rate. So the only input we really took was the location of our source zone, the location of our hazard point, and the potential slip value of permutations.
That's a great question. So yes and no. So if we can compute the exact level set, if we can easily find all those axes that are definitely above the threshold and definitely below the threshold very easily, then that's just a matter of just evaluating the P function. In practice, we're not going to find exactly every point that is above and below the threshold. There will always be that uncertainty region. And because of that, then you might have to do some important sampling with sort of that larger set and use that lower function, the lower approximation of F. And then you will have to do that importance weighted sampling and sample from P restricted to that set. And in that case, how close that level set is to the true level set and the functional formula P will matter. But roughly, to the first approximation, no. Basically, we've moved all of the complexity of the problem into learning function F and taken it away from how small and rare that probability P is. Because that was the main intention. Like, we want to not have a dependence on how rare these events are, because we are interested in estimating extremely rare events.
All right.
Yeah,
go ahead.
Just a quick step back, just to understand the big picture here. So is this some like a way to like circumvent sort of these physics-based simulations that you approximate in data, or is that kind of the idea? In a big picture.
Yeah, so we can talk about the case study part. So as we mentioned, the PTHA has two main sides to it. One is the physics-based simulation, and usually the majority of your info comes from the physics-based simulation of onshore situations. And so the way you make those is like you pick a very small sliver of land, you basically model essentially all the obstructions you'll have in that small sliver of land, and then run the simulation for some earthquake scenario. The problem is, let's say you run a simulation on an earthquake scenario that doesn't even get close to land. You still set up, like it still costs you a certain amount of computation to start that simulation, and you basically lose it if your subset of earthquake scenarios that you're taking from are bad. So the situation we set up is that Melk will sample all things that from an offshore situation, which are roughly easy to compute. You'll pick a very small number of samples that you can transition into trying to do offshore or trying to do onshore simulations. The value from that is that offshore is relatively smooth and quite easy to model and compute and also learn based off of Melk's reinforcement learning techniques. The onshore part, we don't have the time to take 6,000 samples necessarily. And also because there's a lot of obstructions and it's quite case specific, learning that function will be a lot more like, it won't be as continuous as using an offshore simulation. So the main benefit of us is that we reduce our size quite a lot before we start transitioning to onshore with a lot less cost to do that reduction.
Great, I think we're at a time. Thank you so much for joining today. The next time we'll have the last seminar in the series. And we'll see you next time. Thank you.
Great job.